Okay, so welcome back. We continue with our study of A star and its variations. We have seen that we can view the whole thing in a generalized framework where f of n is equal to g of n plus w into h of n, and we saw some impact of the weight in the sense. Now, let us focus on admissible variations of A star, which are linear in terms of space requirements, and we will see later on that in this century and perhaps a little bit earlier, the need to explore very large graphs was presented by problems that came up from different areas of research essentially. In particular, the task of sequence alignment from bioinformatics, and we will look at that very briefly before we in the next session essentially, before we move on to other variations. So, but we first look at admissible variations which came in the last century, and the goal you must remember is to cut down on the space complexity of the algorithm. Now, this is something that we have already seen. We saw the two versions of A star, A1 and A2, where one heuristic function H2 of n was more informed than H1 of n, and we saw that the space explored by A2 is contained in the space explored by A1, which means that it will not only finish faster, it will also use up less space. Then in the last session we saw that we can use weighted A star, which can further shrink the space that is explored by the algorithm, but we have the danger of losing admissibility, as was illustrated in the example that we saw in the last session. Now, let us look at variations which are still admissible essentially, and we want to cut down on space because empirically, and this is something that this is a graph that we saw when we were looking at best first search. We said that the open list for best first search also tends to be exponential in nature, even though it may not be as bad as that of breadth first search. Breadth first is definitely exponential, depth first was linear, and best first we said that by and large tended to be exponential, but we also made the observation that its performance depends upon how good the heuristic function is. Then we saw that A star in general needs more space than best first search, and we saw that in the last session when we compared A star with best first search, and not only with best first search with branch and bound and W A star. So, A star in general needs more space than best first search, and best first search itself can tend to be exponential if the heuristic function is not particularly good. So, let us look at variations of A star which require less space. So, we want to save on space, and this will be our focus for the next few sessions. So, this is what I just said, that while studying best first search, we had observed that the space complexity of the algorithm is often exponential, and it really depends upon how good the heuristic function is essentially. This led us, when we were studying best first search, to look at local search algorithms. We started with hill climbing, then we went on to beam search and taboo search and simulated annealing. So, this should be taboo search. And simulated annealing, and later on we also moved on to population based methods like genetic algorithms and ant colony optimization. But we also saw that these algorithms do not guarantee optimality, though algorithms like genetic algorithms, simulated annealing, ant colony optimization often give you very good solutions, but at the moment we are focusing on guaranteeing optimality. So, the question we want to ask is, are there space saving versions of A star that are also admissible? Perhaps at the expense of time complexity, and if you remember what we did when we studied depth first iterative deepening, we said that we can trade off space versus with time and get a algorithm which requires much less space, and the first algorithm that we will see is in fact an extension of DFID, or depth first iterative deepening. So, just to recap, we started with doing depth first iterative deepening by first writing an algorithm called depth bounded DFS. Depth bounded DFS simply says that there is a bound beyond which depth first search cannot go, and you simply do depth first search within that bound. The bound is shown in this example in a circle which is shaded. So, you do depth first search only up to that bound, whatever that bound is, D in this case, and it requires linear space. Why? Because it is depth first search, and we had seen that the open list for depth first search grows only linearly, but it is not complete. No, that as you can see, if it is going to stay within this bound, it is not even going to find a path to the goal. Forget about guaranteeing a shortest path essentially. So, it is neither complete nor admissible, which is a property of depth first search. But depth first iterative deepening, essentially what it does is that it does a sequence of depth first searches, and in every iteration it increases the depth bound by 1 essentially. So, this was depicted in this here, that after you have done the depth bounded DFS up to a certain depth, if you have not found the solution, increase the bound by 1 and then again do DFS. So, it was a sequence of DFS searches of increasing bound, a sequence of depth bounded depth first searches, because each of these depth first searches was bounded by depth, and therefore, they required linear space because they were essentially depth first search. But when the path to the goal is found in some iteration, it is the shortest path, because otherwise it would have found the path in the previous section if there was a shorter path to a goal. So, in that sense, the behavior of DFID was like breadth first search, but internally it was like depth first search. Of course, we had to do a sequence of searches, and we had done a little bit of analysis about how much is this extra work that we do in DFID, and we had come to the conclusion that for a search space which grows exponentially, the extra cost was insignificant essentially. It was only B over B minus 1 times the value of what breadth first search would have done essentially. So, it is clearly a motivation for devising a new algorithm, and this new algorithm is called iterative deepening A star. The algorithm was given to us by Richard Korf in 1985, and it is designed to save on space by doing a series of depth first searches of increasing depth, exactly like DFID. Unlike DFID, which uses depth of the node as a parameter, remember that when we were studying DFID and depth first search and breadth first search, we did not have edge cost. So, our notion of optimality was the length of the path, but now edges have cost associated with them. So, length of the path may not be the right idea, as we have observed that we have to have a different way of measuring the cost of the solution found. So, DFID was an extension of breadth first search, or rather it was depth first search trying to behave like breadth first search. In a similar manner, IDA A star is going to be depth first search trying to behave like A star essentially, and what it will do is that it will use f values to determine how far the depth first search should go. So, in all these variations DFID, IDA star, it is essentially depth first searches of increasing bound. It is just that how the bound is determined is different in the two cases. IDA star initially sets the bound to f of s, which is equal to h of s, if you remember, because g of s is 0, and we know that h of s is an underestimating functions, which underestimates the optimal cost, and so it will never find a solution. Depth first search will never venture into a solution which is more expensive than the optimal solution, because it starts off by looking at depth only where at best a solution can be found. At best h of s can be equal to h star of s, and if that happens to be the case, then it will find the solution. In subsequent cycles, it extends the bound to the next unexplored f value. Now, this is different from DFID. In DFID, we just increase the depth by 1, but here we are extending the path length to the next node that we have not explored. We will see that this may cause problems of its own, but let us first look at the algorithm itself. So, iterative drifting A star has starts with a depth bound of f of s, and exactly like in the previous case, it does depth bounded depth first search. If the search fails to find a path to the goal, it increases the depth bound, but this time it increases it to the f value of the next cheapest node that was not expanded in the last round. So, it does a sequence of with increasing depth bound, thus requiring linear space as before. Everything else does not change. The argument which says that it will find an optimal path is the same as the argument that we gave in DFID, because when a path is found in some iterations, it must be the shortest path, because otherwise it would have been found in the previous iteration. So, this is how DFID is a variation. IDA star is a variation of DFID. DFID was depth first trying to behave like breadth first, because breadth first gave you the shortest path in terms of number of hops or the length of the path. In IDA star, the same thing is happening, increasing number of depth first searches, but now it is trying to behave like A star, because it will find us the shortest cost path, where the cost is the sum of the edges, sum of the cost of the edges in the path that is found. Okay. So, if you were to look at the space explored by IDA star, this diagram shows you that at any given cutoff or depth bound, which is shown by this gray colored oval arrow, the space that IDA star explores is shown in this green colored nodes, and you can see that there are many ways of reaching different nodes, but what IDA star will do is that it will do a depth first search, which means it will go down this path, then it will backtrack, go down this path, then it will backtrack, go down another path, and so on. So, essentially it will do depth first search, but it will stay within this boundary. So, this green node is not the list of closed nodes, it is a list of nodes which have explored by DFS, and we have said that DFS will require only a linear amount of space. The nodes in the yellow are the ones which were generated, but which were outside the bound, and therefore, they were not inspected. And what IDA star will do, that it will take the cheapest of those nodes. For example, in this example it could be this one, and it will extend the boundary to that f value of that node. So, in that sense it is a little bit different from DFID. DFID extended the depth by 1. IDA star increases the bound to the value of the cheapest unexplored node, f value of the cheapest unexplored node. Now, that can lead to problems of its own, as you can imagine. Even when the state space grows quadratically, which means that you are looking at a city map or something, where the area increases as your search space increases, which is the square of the length, then the number of paths to each node will grow exponentially, because it is a combinatorial problem, and we will see that this same combinatorial problem will crop up when we are talking about sequence alignment, and which is one reason why we will focus on space saving algorithms. Because the number of combinations grows exponentially, the depth first search algorithm, and we saw this in the example of DFID, can explore many different paths to the same node, especially when the closed list is not maintained. And we had argued that if you maintain the closed list, then in DFID we cannot guarantee the optimal path. So, we had said that in DFID you should not maintain the closed list. So, if you are not maintaining the closed list, then repeatedly visiting the same nodes again and again is going to be a problem. But it is also a problem that IDA star extends the path only to the next unexplored node. Now, in the case of DFID, because it was depth that we were looking, and we could think of the tree as a layered tree, and you go to level 1, then to level 2, then to level 3 and so on. At each level you would include many new nodes, but in the case of IDA star, because we are only incrementing the value to the next f value, it is possible that only 1 or 2 or 3 nodes may come into the ambit of the next cycle, which means that the number of cycles may be very many essentially. So, this is a major problem with IDA star, and we have had students who have implemented IDA star and they have observed this behavior that the number of cycles which happens in a randomly generated graph can be quite large essentially. So, one option that we can look at if you are implementing IDA star, because after all IDA star has the advantage of giving you linear space, is to not increment it to the next f value, but choose some value constant and say I will increment it by that much, and of course, you may have to pay a price in terms of optimality. So, this diagram depicts this situation where you are incrementing the bound by a certain pre-decided value delta, and then you will do depth first search by this path. So, what does this mean? It has this implication that if it is again searching like this, going down this path, in fact, in this case it is going to be like going up to the new bound, it may first hit this goal node, which is actually less, which has a greater cost than another node which would have occurred later, because the search is sweeping in this direction, and it may miss out on this particular node, it will miss out on this node, but it will find this node which is actually a little bit more expensive. But the extra cost is bounded by delta, and if you are willing to pay that much price, then our IDA star is going to speed up much more than the basic IDA star algorithm. But Richard Koff, the person who gave us IDA star, also gave us a new algorithm called recursive best first search, and we have seen that IDA star has linear space requirement because it is depth first in nature, but it has no sense of direction, again because it is simply depth first in nature. Recursive best first search is an algorithm given to us by Koff in 1991, and in his words he says that RBFS is a linear space best first search algorithm that always explores new nodes in best first order. So, in some sense it has a sense of direction, and he observes that it expands fewer nodes than iterative deepening, and by this he means iterative deepening A star with a non decreasing cost function. So, RBFS is a little bit like hill climbing with backtracking, that you go down some path requiring linear space, because hill climbing requires linear space. Hill climbing requires constant space, but if you maintain the parent pointers, then you would if you maintain the path backwards, it would require linear space with that, and you backtrack if no child of the current node is the best node on open essentially. So, it is a bit like hill climbing where the candidates have been of the parents have also been kept alive, they have been kept in open, and for the current node, if the neighbors does not contain the best node, then you backtrack. But actually backtracking would mean increasing amount of space. RBFS does not backtrack, it does what they call as rollback. By rollback you mean you just undo what you did and go back to some ancestor, and the ancestor is the one which is a sibling of a node which has been marked as the second best node. So, rolling back by itself would not help, because then you would come back to the same path, because the values f values are the same. So, what RBFS does is that it backs up the lowest value for each node and updates the values of its parents as it rolls back. So, this is a key feature of RBFS, that it rolls back and updates the value. So, let us see that with an example. We will not discuss the algorithm in much more detail here, and let us say this is the case where the nodes in pink are, they depict the path that is generated by A star. So, you see we start with a value of 50, these are f values, and we will see in the next session that typically f values tend to increase as we go towards a goal, but we will do this a little bit more formally especially under some conditions that we will study, which is called the monotone criteria. But in general, the f values tend to increase because they tend to become more accurate, because the contribution of h decreases as you are going closer to the goal. So, this is a value. You start with a value of 50, then you have 3 children 59, 50 and 82. You choose 55 there and you mark 59 as the second best. So, this one is the second best and it is marked and we have it in this color. Then you keep progressing, you generate the children of 55, you have 61, 61, 56, you choose the best as long as it is better than the second best. This process goes on, you come down to another 56, then 57, then 58 and then suddenly when you generate the children of this node 58, you find that all of them are worse than the second best node 59. Now, remember that observe that the space requirement here is linear, because at every level as you go down you just add a constant number of neighbors, which is what depth first search would have done. Unlike depth first search, what this one is doing is that it has a sense of direction. So, it is not going to the leftmost path, but it is going to the path which is guided by the heuristic value. So, in that sense it is a little bit like hill climbing, but it is more like depth first search in the sense that it maintains all the parents and their children. And in this particular example, when it finds that hill climbing would not have proceeded, well, in a sense that it is not like hill climbing, because the neighbors are, the next nodes are actually increasing f values and we have seen that. So, that condition that the neighbors have to be better than current node is relaxed here. You move to the best neighbor, but RBFS also keeps a second criteria, which is that you must be better than the second best node that we have seen so far in this case, which is a value of 59. Now, all the 3 nodes generated here at the bottom, they have a value of 63, 61, 62, all 3 are worse than the second best. So, RBFS simply rolls back this entire search tree, but when it rolls back, it updates the values of its parents as it does so, and it backs up the best value for every parent. So, this last node 58 now becomes 61, because 61 is the best value that it can find amongst its children. Then between 64, 60 and 61, this 60 gets backed up to its parents. So, 57 gets updated to 60 and so on. So, this process goes, this 60 is again propagated back and propagated back and propagated back all the way up. So, this node which was 55 has now become 60 and search resumes from this point onwards. So, at this point when it has rolled back, you can see that the middle node has become a value of 60. Now, the left node has a value of 59 and so the new search starts from there. So, it goes along these paths and it will roll back as and when necessary, maintaining linear spaces. So, this is the RBFS algorithm which we have done rather quickly. I will leave you with an example here, a problem for you to solve. In this example, these nodes are the closed nodes that have been explored. The nodes with single circles are open nodes that are in open, and the nodes in dashed circles are the ones which have yet to be explored, and you should look at which of them you want to explore. And the values are f values, and what I would like you to do is to draw the graph after 2 expansions have been done from this given state, and also mark where the third node that RBFS will pick up. So, we will put up this graph as part of the weekly assignment and you must try to solve this problem. Next, we will look at what is called as a monotone or consistency condition, when A star will behave like Dijkstra's algorithm, which means that when it puts a node in closed, it would have found an optimal path to that node, or in other words, when it picks a node from open, it would have found an optimal path. And we will see that this monotone criteria will allow us to write better space saving algorithms, which in fact were devised in this century. So, we will take that up in the next session. So, see you then.